You're about to step inside massive Chinese factories where millions of oil pipelines are made at a scale almost impossible to comprehend. Every single day, these facilities push out enough pipeline to stretch for miles, feeding energy systems that power entire countries. Some of these plants produce over 1,000 tons of pipe daily, enough to lay a pipeline longer than a full marathon in just a few hours. You heard that right. And every one of those pipes is expected to survive extreme pressure, violent temperature swings, and decades buried underground without failing. But this is where it gets serious, because one microscopic defect, one flaw you could never see with your eyes, can trigger a rupture that shuts down entire sections of pipeline across miles of terrain. And it wasn't just the pipe that would fail. The pressure inside it would turn that weakness into a chain reaction. So now you're looking at something much bigger than manufacturing. You're looking at a system where speed and precision have to exist at the same time, where thousands of pipes are produced daily, yet every single one has to perform as if it's the only one that matters. So how do these factories actually pull this off, at this scale, without things falling apart? You're about to follow the entire journey from raw steel to high-pressure pipelines and see exactly how this system holds together under pressure. Massive industrial scale. You step deeper into the factory, and the first thing that hits you is the scale. This isn't a single production line quietly moving in one direction. It's a network of synchronized systems, each one running at full capacity, each one feeding into the next without pause. Steel moves in, finished pipelines move out, and the entire process never slows down. Overhead cranes slide across the ceiling carrying coils that weigh as much as a fully loaded truck. Sparks flash from welding stations in the distance. Conveyor systems stretch so far you can't see where they end. And every few seconds, another section of pipe rolls forward, identical in shape, but destined for a completely different part of the world. Some of these factories operate around the clock, producing thousands of tons of pipeline every single day. That adds up to miles of pipe leaving the facility before a single shift ends. You're watching an operation that doesn't think in units. It thinks in infrastructure. But the real pressure isn't the speed, it's the consistency. Because at this scale, even the smallest deviation multiplies instantly. A minor misalignment here doesn't stay small. It becomes hundreds of flawed pipes within hours. And it wasn't just the machines carrying that burden. Entire teams monitor every stage, watching data in real time, adjusting systems before problems even appear. Every movement, every cut, every weld is tracked, measured, corrected. Because once a pipe leaves this building, there's no room for error. But this entire operation depends on one thing, arriving perfectly every time. Raw steel. Raw steel foundations. You watch as massive steel coils are unloaded and lined up with precision, each one weighing several tons and tightly wound like a compressed spring. At first glance, they look identical, but they aren't. Each coil is engineered for a specific purpose, with a carefully controlled mix of carbon and alloying elements that determine how the final pipe will behave under pressure. Before anything else happens, the steel is inspected, surfaces are scanned, edges are checked, and any imperfection is flagged immediately. Because once this material enters production, there's no turning back. Every flaw that goes unnoticed here will be carried forward into the final pipeline. The coils are then unrolled and fed into leveling machines that flatten the steel into perfectly uniform sheets. You can hear the tension in the metal as it straightens, forced into alignment under immense pressure. This step looks simple, but it sets the foundation for everything that follows. Then comes trimming. The edges are cut with exact precision, ensuring that when the steel is later formed into a cylinder, those edges will meet flawlessly. A fraction of a millimeter off here can create a weak point that no amount of welding can fully correct. And it wasn't just about shape. Chemical consistency matters just as much. The steel has to respond predictably to heat, stress, and pressure. If it doesn't, the entire pipeline becomes unreliable, because this material won't stay in a controlled factory. It will be buried underground, exposed to moisture, pressure, and time. And once it leaves, there's no second chance to fix it. But shaping flat steel into a pipeline that can carry oil for thousands of miles requires something far more complex. Forming the cylinder U Follow the steel sheets as they move into the forming line. And this is where flat material begins to take on its final purpose. The transformation doesn't happen all at once. It happens gradually, through a series of rollers that bend the steel step by step, guiding it into a perfect cylindrical shape. At first, the change is subtle. The flat sheet curves slightly at the edges. Then more rollers press in, increasing the curvature until the steel begins to resemble an open pipe. By the time it reaches the final stage, the edges are aligned so precisely they appear almost fused together. But this is where the pressure builds, because alignment here is everything. If those edges don't meet perfectly, the weld that follows will carry hidden stress, and that stress doesn't show up immediately. It shows up later, under pressure, when the pipeline is already in use. Different methods are used depending on the type of pipe being produced. Some lines rely on high-speed electric resistance forming, where heat is generated through electrical current. Others use large-scale submerged arc systems, designed for thicker, high-pressure pipelines. The machines adjust automatically, responding to the thickness and specifications of each sheet. You're watching a process that adapts in real time, maintaining precision even as materials change. And it wasn't just the shape that mattered. The internal structure of the steel is already being affected by the stress of bending. Too much force, and microfractures can form. Too little, and the pipe won't hold its shape. Every second here is a balance. Because once the cylinder is formed, there's only one thing holding it together. And that's where the real risk begins. Welding under pressure. You watch the open cylinder move forward, its edges now perfectly aligned. And this is where everything becomes irreversible. Because the moment welding begins, that seam becomes the single most critical point in the entire pipeline. The process starts with intense heat. In some lines, a high-frequency electrical current runs through the edges, generating enough heat to fuse them together instantly. In others, molten metal is deposited along the seam using submerged arc welding, creating a bond designed to handle extreme internal pressure. From a distance, it looks controlled. Up close, it feels violent. Sparks burst outward in controlled arcs. The metal glows, softening just enough to merge into one continuous structure. And as the pipe moves forward, the weld forms in real time, sealing the cylinder completely. But this is where the tension rises, because a weld can look perfect on the surface and still fail under pressure. That's why the process doesn't rely on a single pass. Internal welding reinforces the inside of the pipe, while external welding strengthens the outer seam. Sensors monitor temperature, speed, and alignment at every moment. If anything drifts even slightly, the system corrects it immediately. And it wasn't just about joining metal. It was about creating a bond that could survive decades of stress without weakening. Because once oil begins flowing through this pipe at high pressure, that seam becomes the line between stability and rupture. But even a perfect weld doesn't guarantee strength, because the structure of the steel itself still has to be transformed. Heat that transforms steel. You follow the pipe as it moves into the heat treatment zone, and the environment changes instantly. The noise fades into a deep mechanical hum, replaced by the steady roar of massive furnaces glowing with controlled intensity. This is where the pipe is pushed to its limits on purpose. The steel is heated to extremely high temperatures, altering its internal structure at a microscopic level. At this stage, strength isn't added from the outside, it's built from within. The arrangement of atoms shifts, allowing the material to handle stress in ways it couldn't before. But the real challenge isn't heating the pipe, it's controlling how it cools, because cooling too quickly can make the steel brittle, increasing the risk of sudden fractures. Cooling too slowly can leave it too soft, unable to withstand the pressure it will eventually carry. So the entire process is carefully timed, balancing temperature, airflow, and duration with extreme precision. You're watching a transformation that determines whether this pipeline survives years or fails under pressure. And it wasn't just about strength. Flexibility matters just as much. These pipes will expand, contract, and shift once they're installed. If they can't adapt, they crack. Every second inside this furnace decides how the pipe behaves in the real world, because once it leaves this stage, its properties are locked in. But even a perfectly treated pipe faces a threat that never stops working against it, fighting corrosion layers as the pipe exits the heat treatment line. It looks finished, smooth, solid, and strong. But in reality, it's still vulnerable. Because the moment this pipe is exposed to the environment, corrosion begins. And corrosion doesn't happen all at once. It starts slowly, silently, weakening the material over time until failure becomes inevitable. That's why the next stage focuses entirely on protection. The pipe moves through coating systems where multiple layers are applied with precision. First, the surface is cleaned again, removing any contaminants that could prevent proper bonding. Then, protective coatings are added, often epoxy-based layers designed to resist moisture, chemicals, and soil conditions. For more demanding environments, additional layers are applied. Polyethylene coatings wrap around the pipe, creating a barrier that shields it from harsh surroundings. Internal coatings may also be added, reducing friction and allowing oil to flow more efficiently through the pipeline. But this isn't just about durability. It's about survival. Because these pipelines will be buried underground, submerged in seawater, or exposed to extreme climates. Once installed, inspecting or repairing them becomes incredibly difficult. And it wasn't just the environment working against them. Temperature changes cause expansion and contraction. Moisture seeps into the smallest imperfections. Over time, even strong steel begins to weaken, unless it's protected. So every layer applied here acts as a defense system, extending the life of the pipeline for decades. But even after all this, the pipe still hasn't earned the right to be used. I inspected to perfection. You follow the pipeline into what might be the most unforgiving stage of all. Because this is where the pipe is no longer shaped, welded, or treated, it's judged. Every inch is examined using systems designed to detect flaws too small for the human eye to see. Ultrasonic testing sends high-frequency sound waves through the metal, revealing hidden cracks or inconsistencies deep inside the structure. Then come X-ray scans, exposing the weld seam in precise detail. What looked flawless before is now analyzed layer by layer, searching for voids, weak spots, or imperfections that could grow under pressure. And this is where the tension peaks, because failure here doesn't mean repair, it means rejection. Pipes that don't meet exact standards are removed immediately, no matter how close they were to completion. There's no compromise, because once these pipelines are deployed, failure doesn't stay contained. It spreads across miles. Hydrostatic testing pushes things even further. The pipe is filled with water and pressurized beyond its intended limits. If it holds, it moves forward. If it doesn't, the weakness is exposed instantly. And it wasn't just machines making these decisions. Advanced systems now use AI-driven analysis to detect patterns, predict failures, and ensure consistency across thousands of pipes. You're watching a process where perfection isn't a goal, it's a requirement. Because once a pipe passes this stage, it's no longer just a product, it's part of something much bigger. And what it's about to face next is far more extreme than anything inside this factory. Built for extremes, you follow the finished pipes as they move out of inspection, and for the first time, you realize something important. Everything you've seen so far, all the precision, all the testing, all the control, it was only preparation. Because these pipes were never built for this environment. They were built for the harshest conditions on Earth. Some of them will be buried deep beneath deserts, where temperatures swing from freezing cold at night to intense heat during the day. Others will be laid across frozen ground, where shifting ice can bend steel over time. And some will be lowered into the ocean, where crushing pressure and salt water work constantly to break them down. And it wasn't just the environment that creates risk, it's the pressure inside. Oil and gas don't move slowly through these pipelines. They are pushed across thousands of miles under extreme pressure, forcing the pipe to handle continuous internal stress without weakening. Every inch of that pipeline is under load, every second it operates. So the design changes depending on where the pipe is going. For high-pressure crude oil lines, the walls are made thicker, built to contain force that would otherwise rupture standard steel. For gas pipelines, flexibility becomes critical, allowing the pipe to expand and contract without cracking. Offshore pipelines require specialized coatings and alloys that resist corrosion even in salt-heavy environments. And then came the most unpredictable threat of all: movement. Pipelines don't sit in perfectly stable conditions. The ground shifts. Soil settles. Earthquakes send stress through entire sections of pipeline. If the material can't absorb that movement, it fractures. That's why some pipes are engineered with controlled flexibility, allowing them to bend slightly under stress instead of breaking. Others use reinforced joints that distribute pressure across a wider area, reducing the chance of failure at a single point. You're looking at a system designed for survival, not comfort. Every decision from thickness to coating to flexibility is based on one question: will this pipe still function after years of stress no one can control? Because once it's installed, there's no easy way to fix it. Repairs can take weeks. Failures can shut down entire energy networks. And in some cases, the damage spreads far beyond the pipeline itself. But even with all this engineering, the scale of what these factories produce is far bigger than any single pipeline. And it wasn't just one country depending on this system, powering global networks. You step back and begin to see the bigger picture. These pipes aren't staying here. They aren't built for one region, or one project, or one country. They are shipped across the world. From this single factory, pipelines are sent to deserts in the Middle East, frozen regions in Central Asia, offshore rigs in deep oceans, and expanding energy networks in developing economies. What starts as raw steel inside this building becomes part of infrastructure that stretches across entire continents, and the scale keeps building. Factories like this don't produce in small batches. They produce continuously, feeding massive global projects that require hundreds, sometimes thousands of miles of pipeline. Entire energy corridors depend on this output. Without it, oil fields can't connect to refineries. Gas reserves stay trapped underground. Energy supply chains break before they even begin. And it wasn't just about volume, it was about speed, because global demand for energy doesn't slow down. Countries expanding their infrastructure need pipelines delivered on tight timelines. Delays don't cost hours, they cost millions. So these factories are designed to meet that demand, producing at a pace few others can match. That's where China's manufacturing dominance becomes impossible to ignore. The combination of scale, automation, and supply chain control allows these facilities to operate at a level that reshapes global competition. Raw materials arrive faster, production moves faster. Delivery happens at a scale that supports entire international projects. But this was just the visible part of the system, because behind every pipeline shipped out, there's an entire network of coordination logistics, engineering standards, inspections, and compliance with international requirements. These pipes aren't built randomly. They are designed to meet strict global specifications, ensuring they can integrate into systems anywhere in the world. And it wasn't just energy companies relying on this. Entire economies depend on the flow of oil and gas through these pipelines. Transportation, electricity, industry, everything connects back to this hidden network running beneath the surface. You don't see it when you turn on a light or fuel a vehicle, but it's there. Miles and miles of pipeline, built to operate without failure, carrying energy across distances most people never think about. And every one of those pipelines started in a place like this, where steel is shaped, tested, and perfected at a scale almost impossible to comprehend. Because behind every system that powers the modern world, there's an industry built to keep it running, no matter what. Where it all connects you, step back from the production lines, and for a moment, everything feels quiet. The machines are still running, pipes are still moving, but your perspective shifts. Because now you see what this place really is. This isn't just a factory producing steel pipes. It's building the hidden system that keeps the modern world running. Every pipeline you watched being formed, welded, treated, and tested will disappear once it leaves here, buried underground, laid across ocean floors, stretched through mountains and deserts, where no one will ever see it again. And that's the point. Because these pipelines aren't meant to be noticed. They're meant to work. Oil will move through them for thousands of miles without stopping. Gas will travel across entire countries, feeding power plants, industries, and cities that rely on a constant, uninterrupted flow of energy. And most people will never think about how that flow is maintained. But this was just the beginning of what's at stake. Because when these pipelines fail, the consequences don't stay hidden. A single rupture can shut down supply across entire regions. Pressure drops instantly. Energy networks struggle to compensate. And in the worst cases, the damage spreads far beyond the pipeline itself. That's why everything you saw inside this factory carries so much weight. Every weld, every inspection, every layer of protection exists to prevent that moment from ever happening. And it wasn't just about avoiding failure. It was about maintaining trust, because global energy systems depend on reliability. End quote. Countries invest billions into infrastructure that has to perform for decades. There's no room for uncertainty, no margin for error. Once these pipelines are installed, they become part of a system that cannot afford to stop. So what you're really looking at isn't production, it's precision at scale. A process where millions of pipes are created, yet every single one is treated like it cannot fail. Where speed and volume exist side by side with extreme control. Where the smallest detail carries the same importance as the largest system. And that's what makes this entire operation different, because it's easy to focus on the size of these factories, the machines, the output, the scale. But the real story is something else. It's the fact that behind all that scale, every single pipe still has to be perfect, because once it leaves this place, it doesn't get a second chance. The final reality. You've seen the scale. You've seen the machines. You've followed the process from raw steel to a finished pipeline, ready to be deployed across the world. But now comes the part most people never stop to think about. What all of this actually means. Because every pipe that leaves this factory is built with one expectation. It has to work every second, for decades. There are no pauses once it's installed. No easy repairs. No second chances if something goes wrong. Oil keeps moving. Gas keeps flowing. Pressure never disappears. And the environment around it never stops pushing back. And that's where the real weight of everything you've seen starts to settle in. Because this entire system depends on something incredibly disrespecting. Simple. Trust. You're trusting that a pipeline buried miles away, built in a place you've never seen, is operating exactly as it should, that every weld held, that every layer of coating stayed intact, that every test caught what it was supposed to catch. But this was just the beginning of that responsibility, because the further these pipelines stretch, the more that trust expands. Entire cities rely on it. Industries depend on it. Energy systems are built around it. And none of it works if even a small part fails. And it wasn't just the pressure inside the pipes that matters. It's the pressure on the system itself. Demand keeps growing. Infrastructure keeps expanding. More pipelines are needed across more extreme environments, under tighter timelines. And that means these factories have to keep pushing further, producing faster, maintaining precision, scaling without losing control. That balance is where everything becomes difficult. Because producing millions of pipes is one challenge. Producing millions of perfect pipes is something else entirely. And yet, that's exactly what's happening here. You've watched a process where speed never replaces precision, where automation never removes control, where every stage, from shaping to welding to inspection, is built around one outcome: reliability. Because in the end, these pipelines aren't measured by how quickly they're made. They're measured by how long they last. And that's the part that changes how you see everything. Because behind every drop of fuel, every surge of electricity, every system that depends on energy moving without interruption, there's a pipeline built somewhere like this, engineered to disappear, designed to endure, and expected to never fail.